Thanks for the organizer for this great opportunity. The topic of my talk is about combinatorial characterization for graph rigidity, which is a well-known problem in the rigidity theory. And in that context, there is a also famous long-standing conjecture due to Jack Graber concerning the uniqueness of the unique maximality of generic rigidity matroids. And the goal of this talk is to explain how this unique maximality conjecture is important to attack the combinatorial characterization problem. So this is should the slide be changed? No, not yet. So this is joint work with Katie Clinch and Bill Jackson. So let me start. Okay. So because I'm the first speaker, so maybe I should correct the basic terminology from the graph rigidity. So I will try something. I will explain the basic definition slowly. So suppose we are given the graph in d-dimensional space, Euclidean space. Such a graph is usually called a Barn joint framework in this context. And I will use a notation pair of G and P to denote a Barn joint framework. So here, G is a graph, underlying graph, and P is underlying point configuration. And suppose you have a Barn joint framework. So this is an example of a two-dimensional framework. And in the rigidity problem, we are asked whether there is a continuous deformation of this Barn joint framework. So algebraically, this is equivalent to asking whether there is a non-trivial solution in the system of quadratic equations that describes edge length constraints. So here the P is fixed and X is a variable. And we are interested if there is some non-trivial solution in the neighbor of P. But this is a quadratic system, so usually it is difficult to understand the space of all solutions. So general approach is to look at the first order approximation of this quadratic systems, and then we get this system, which is linear in X dot. So here the P is fixed and X dot is a variable. And this system gives a concept of infinitesimal rigidity. So in the infinitesimal rigidity, we are asked whether there is a non-trivial solution in this linear system. Because this is linear, so we can compute the solution space. So that's good. But because infinitesimal rigidity is a first order approximation of the concept of rigidity, so in general, infinitesimal rigidity is not equal to rigidity. But if we assume that P is generic configuration, then it turns out that infinitesimal rigidity is equal to the rigidity. Moreover, if P is generic, then infinitesimal rigidity is completely determined by the underlying graph. So this fact motivates Asimov and Ross to define the concept of the graph rigidity. So we say that the graph is rigid in RD if any generic Barn joint framework of G is rigid in RD. And because this is a property of graph, so natural question is to give a characterization of rigid graphs in terms of graphs. So this is a combinatorial characterization problem of graph rigidity. Okay. And so the most fundamental tool to attack this combinatorial characterization problem is this Maxwell's count condition. this is for any infinitesimal rigid framework. So this is a necessary condition for the infinitesimal rigidity of any framework. So suppose we have a band joint framework, then it is minimally rigid. If it is minimally rigid in RD, then underlying graph must satisfy the following two conditions. So first condition says that the number of edge is equal to d times the number of vertices minus d plus 1 choose 2. And the second condition says that for any subgraph, the number of edge must be at most d times the number of vertices minus d plus 1 choose 2. So for example, if you look at this two-dimensional framework, then you can check that, so number of vertices is 6 and the number of edges is 9. So we have this condition. But if you look at this subgraph, then this subgraph is too dense to satisfy the second condition. So the second condition is actually violated. So you can conclude that this is actually the infinitesimally flexible. And this is an example of the infinitesimally rigid framework. And you can check that indeed these conditions is satisfied. And this condition is nice because this is very clear combinatorial just relation between the number of edges and the number of vertices. And this condition, this is for any framework. So the condition also should hold for the rigidity of graphs. So you can just say that you can just replace the framework with graph, and we say that you can see that if graph G is minimally rigid in RD, then the Maxwell count condition must satisfy. And what is interesting is interesting question is whether the converse direction of this necessary condition is true or not. And when D is equal to 1, you can easily check that actually this condition is just a cycle freeness of the graph. From which you can conclude that the converse direction is also true because graph is rigid in one-dimensional space if and only if the graph is connected. And the interest case is when D is equal to 2. So actually, even in the two-dimensional space, this condition is also sufficient for the minimal rigidity. So this is well known as the Rahman's theorem. But when D is equal to 3 or more than 3, the converse direction is no longer true. And characterization problem is still open. So this is a basic background of the combinatorial characterization problem for rigidity. And now I hope so far everything is okay. And from now, I would like to move to a little bit more detail. So one of the key tools to analyze this combinatorics of rigidity is the concept of rigidity matroid. So let me introduce rigidity matroid. So this is not a complicated thing. So suppose we have the complete graph with n vertices. And let's take a generic point configuration of the vertices of the complete graph. And we consider the rigidity matrix, which is a matrix representing the linear system I just gave you in the definition of the infinitesimal rigidity. So here is a rigidity matrix. Maybe you don't have to understand the exact entries of the matrix, but one important thing in this definition is that it has the same combinatorial structure as incidence matrix. So for example, in the incidence matrix, you have, so let's say this is incidence matrix, then each row is associated with an edge. And each column is associated with a vertex. And if HE links between VI and VJ, then you have a 1 and -1 here. And remaining entries in this row are 0. But in the rigidity matrix, you have the same combinatorial patterns, but the difference is just here. Instead of 1 and -1, you have PI and PI minus PJ and PJ minus PI, which is a direction of the edge in the framework. And important things in this definition is that each row is associated with an edge. So if you look at the row matroid in this matrix, then you can get a matroid on the edge set of the complete graph. So that's a rigidity matroid, generic D-dimensional rigidity matroid. So generic rigidity matroid is just a combinatorial structure of the row dependence of the rigidity matrix. And this means that the bases are corresponding to the minimally rigid graphs, and circuits are minimally dependent graphs. And independence in this matroid means stress freeness in terms of the rigidity. Okay, and advantage of introducing this rigidity matroid abstract concept is that we can compare the combinatorial structure of rigidity with existing non-discrete structure from the combinatorics. That's an idea of Jack Graber. So he suggested that we might get a better understanding if we study a family of matroids having the representative properties of the rigidity matroid, generic D-dimensional rigidity matroid. And motivated by this, he introduced the concept of abstract D-rigidity matroid. So here is the definition. So let's look at the matroid on the edge set of the complete graph. Then such a matroid is called abstract D-rigidity matroid if it is a KD plus 2 matroid with rank Dn minus D plus 1 choose 2. And what is a KD plus 2 matroid? So matroid is called KD plus 2 matroid if every KD plus 2 is a circuit. So if you consider the rigidity, so in one-dimensional rigidity, triangle is a minimally dependent graph. And two-dimensional case, complete graph with 4 vertices is also the example of minimal dependent graph in 3-dimensional space. K5 is a minimal dependent graph. So those are well known, maybe the most fundamental dependent graph in rigidity, in D-dimensional rigidity. So that can be considered as a fundamental. So having the KD plus 2 as a circuit can be considered as a representative property of the generic rigidity. And also from the Maxwell conditions, the first condition of the Maxwell count, rank of the D-dimensional rigidity matroid is equal to Dn minus D plus 1 choose 2. So this is another fundamental property. And we say that matroid is abstract D-rigidity matroid if it satisfies those two fundamental properties. So I should remark that actually this is not equal to the Graeber's original definition. This is an equivalent characterization due to the Graham, but this formulation will be directly related to our research. I hope definition is clear. And Graeber conjectures that generic D-dimensional rigidity matroid is an extremal example in this family of abstract D-rigidity matroid. And in order to explain this conjecture, let me first introduce the concept of weak order. So here's the definition. So suppose you have two matroids, M1 and M2, and suppose they have same ground set. Then we say that M1 is at most M2 if any independent set in M1 is also independent in M2. So using this definition, so for any family of matroids having a common ground set, we can form the poset with respect to this weak order. And let's consider the family of all abstract D-rigidity matroids on Kn. Graeber conjectures that generic D-dimensional rigidity matroid is a unique maximal element in this poset. That's Graeber's conjecture. We can formulate a slightly stronger form conjecture, which asks whether the generic D-dimensional rigidity matroid is a unique maximum KD plus 2 matroid. So recall that the abstract rigidity matroid is a matroid having the two properties. Every KD plus 2 is a circuit, and also the rank is dn minus d plus 1 choose 2. And so this family of KD plus 2 matroids is a slightly larger family of matroids. And he proves that when D is at most 2, conjecture is correct. But it turns out that this conjecture is false if D is at least 4. But still the conjecture is open in 3-dimensional space. This is a long-standing open problem. And you will see how this conjecture is important for characterizing the 3-dimensional rigidity matroid. Okay. And this Graeber's conjecture, this is the conjecture I have shown you in the last page. And this conjecture consists of 2 parts. So the first part says that there is a unique maximal element in the weak order poset of all abstract D-rigidity matroid. And the second part says that this unique maximal element is attained by the generic D-dimensional rigidity matroid. And this first part can give also nice question. So that's, I would like to say, weak Graeber's conjecture. So namely, the poset of all abstract D-dimensional D-rigidity matroid has a unique maximal element. Again, a stronger form is that the poset of all KD plus 2 matroid has unique maximal element. And for this weaker form, we could prove that the conjecture is correct in 3-dimensional case. And if D is at least 4, then this conjecture is still open. So still there is no counterexample for this conjecture. There's a question. Why is that stronger form? Stronger form of yeah, you are right. Maybe this is independent. Sorry. Yeah, you are correct. Maybe another related conjecture. I should have said this is another related conjecture here. Thank you. So yes, may I move to the next page? Yeah. So let me explain the little bit detail about this counterexample for the strong Graban's conjecture due to Walter Whiteley. Because it turns out that this matroid, his matroid, is a key to understand the structure of the DDGT matroids. So Walter Whiteley found a very interesting matroid from the study on bivariate splines in approximation theory. And this matroid, unfortunately, I do not have time to explain this background. But the definition of this matroid is not very difficult if you know about the rigidity matroid. So it is again defined by using a matrix, and this matrix is called cofactor matrix, and the cofactor matrix is almost same as the rigidity matrix. So the same combinatorial structure, but this time, instead of Pi minus Pj, we have different entries. And this is the entries. You don't have to remember those entries. Just this has a different entries. And important things again is that in this matrix, each row is associated with an edge. So you can define, by using the row matroid, you can define the matroid on the edge set of the complete graph. So this matroid is called S cofactor matroid. So S is a parameter, like a dimension. But it's slightly different from D, as you can see, as you will see. And what is interesting is that the S cofactor matroid is an abstract S+1 rigidity matroid. So this cofactor matroid is from the study on splines. So it's a very hard. It seems that this observation is hard to understand, but this is not super surprising, because so if you look at the case when S is equal to 1, then 1,0 spline over plane graph is a piecewise linear function, which can be considered as a polyhedral lifting over plane graph. And by well-known Maxwell-Kremer correspondence, such a lifting has a one-to-one correspondence with self-stress. From this observation, you can see that one cofactor matroid is equal to the two-dimensional rigidity matroid. So the question is whether this falls for any S. So which means whether there is a non-linear version of the maximum Krömer correspondence in the generic sense. But unfortunately, you don't have any such a nice relation. So Walter observes that when S is at least 3, S cofactor matroid is strictly larger than the S plus 1 dimensional rigidity matroid. So in particular, this means that for D at least 4, D dimensional rigidity matroid cannot be the unique maximal abstract D plus 2 rigidity matroid. So this motivates Walter to give a revised conjecture. So he conjectures that the S cofactor matroid is a unique maximal abstract S plus 1 rigidity matroid. And for this matroid, we recently proved that the conjecture is correct when S is equal to 2. So that means 2 cofactor matroid is a unique maximal K5 matroid. So here is the situation. So you have a kind of family of K5 matroids. In this mountain of K5 matroids, the top element is a 2 cofactor matroid. And conjecture, Graber's conjecture is that the 3-dimensional rigidity matroid is also equal to this 2 cofactor matroid. Unfortunately, our technique cannot be extended to the K6 matroids. So we don't know if the cofactor matroid is at the top of the mountain of K6 matroids. And more importantly, we could show that we could show a combinatorial characterization for 2 cofactor matroid. So this means that if the Graber's conjecture is true, strong Graber's conjecture in 3-dimensional space is true, then our combinatorial characterization gives the combinatorial characterization for the 3-dimensional rigidity matroids. Okay. So this is a current state. So let me explain our combinatorial characterization. So our combinatorial characterization will be described by using the concept of proper KT sequence. So let me introduce this. So let's look at the complete graph. And we look at the sequence of edge sets in Kn. And we say that this sequence is proper if every member xi is not completely covered by the preceding edge sets from x1 to xi minus 1. And we say that this sequence is KT sequence if each member is a copy of KT, which is a complete graph of T vertices. And by using this concept, we defined value function for KT, which is a set function defined over the edge set of the complete graph. And for any edge set F, the value of F is defined by this. And yes, this is complicated. So let me explain. So let's look at any proper KT sequence. Then I will first look at the union of given edge set F and union of all edge set appeared in the sequence. And look at the size of this union, and we subtract k, which is the length of this sequence. So here is just one simple example. So let's consider the K3 sequence. And suppose my f is this. And let's look at this sequence, x1, x2, x3, or copies of K3. Then the union is this and this and this. So the union of all edge sets has size equal to 7. And the length of this sequence is -3. So value for this sequence equal to 4. And the value for f is taking is a minimum possible value over all possible proper KT sequence. So this is a bit complicated. At least this is defined combinatorially. And it looks very complicated, but if you try, for example, K3 case, then you'll see that the value this function for K3 is just a rank function of the cycle matroid of the complete graph. It's a graphic matroid. A little bit more complex case is when t is equal to 4, K4 case. But you can see that the value function is a rank function of the generic two-dimensional rigidity matroid. And what we have proved is that when t is equal to 5, value function for K5 is a rank function of the two cofactor matroid. So this gives a good characterization in the sense that the problem of checking the independence in the two cofactor matroid is in the intersection of complex class NP and co-NP. So this gives a certificate for non-rigidity in the two cofactor matroid, like the Raman's theorem. But still, we don't have a polynomial time, efficient polynomial time algorithm to compute the value function. So that's a big open problem. Okay. So this is a first part of my talk. So if there is a question, then I'm happy to answer. But okay, no questions. So maybe let me move to the second part of my talk. So in the last page.
Sorry, Shinichi, there is a question in the chat. Is the polytime algorithm open even for n equals 5?
Yes. So that's a big open problem. So we know that this computation problem is in the intersection of the NP and co-NP. So generally, people believe that the problem in this class admits a polynomial time algorithm. But we don't know how to compute this function. Oh, we have a randomized algorithm because by randomized algorithm, you can check the rank of this matroid. So polynomial time algorithm for the case when n is equal to 5 or d is equal to 5 is a very big progress to understand, I think, combinatorial structure of rigidity.
Wait, before you move on. So the certificate of being dependent is just a KT sequence that gives you a value lower than the size of F.
Yeah. You can compute in polynomial time if you have you can if you have a sequence certificate. Yeah.
So what's the certificate of independence?
It's by Schwarz-Zipfel lemma. So if you have
Oh, okay, yeah, gotcha. So you use the algebraic one for the other side.
Yeah. So the giving the combinatorial certificate is an interesting open problem actually.
Okay, that's what I was. Yeah. Okay, thanks.
Okay, then let's move to the second part. So here we look at the case when we look at the matroids having the property that every KT is a circuit. But you can look at instead of KT, you can look at the general graph H. That's a second part of the topic of the second part. So let me define the concept of the H matroid. So let script H be a family of graphs. Then we said that the matroid on the H set of the complete graph is a H matroid if every member of H is a circuit. And if this script H consists of a single graph, then we just use this H notation H matroid. And here's an example. So in case of the K3, so when H is equal to K3, then cycle matroid is a K3 matroid because any triangle is a circuit in the cycle matroid. But another extreme example is a rank 2 uniform matroid. So in the rank 2 uniform matroid, again, every triangle is a circuit. So this is also the K3 matroid. And another simple example is when H is equal to P4, which is a path of length 3. Then for example, rank 2 uniform matroid is an example of P4 matroid. Maybe wrong. Maybe to correct. Sorry. Yeah, correct. So so if you look at the path of length 3, then this is a circuit. And here is a question. So for a given n and script H, when does the poset of H matroids have the unique maximal element? So this interesting question was posed by Saran and Vince. And if you try, for example, some simple case when, for example, the H is equal to K3, you can see that the cycle matroid is a unique maximal K3 matroid. And in the case of P4 matroids, actually this rank 2 uniform matroid is a unique maximal P4 matroid. And for those simple special case, you might guess that this poset of H matroid always has a unique maximal element. But it turns out that this is not true in general. This is not the case. So the Gula-Papp observes that when H is equal to C5, there are two distinct maximal C5 matrices. So we want to we want to understand what's the difference between, what is the difference between the K3 matroid or K4 matroid and C5 matroid. So in this case, we have the unique maximal element in the poset, and in this case, poset have more than one unique, more than one maximum matroid. And unfortunately, currently, I don't have any complete answer, but still, I conjecture that our value function plays a key role to understand this phenomenon. So let me introduce again our value function. So we define the value function using the KT sequence, but instead of KT sequence, we can use H sequence. So the definition is just a copy of the definition for the KT sequence. So we say that the sequence of H set is H sequence if each xi is a copy of a graph in script H. And value for H can be defined in the same way by using the proper H sequence. Then we can show that for any H matroid, its rank is at most the value function for H. We have this. And this lemma implies that if this value function is a sum modular, and if there is at least one H matroid, then this sum modular function is a rank function of the unique maximal H matroid. So if we can show that the value function is sum modular, then that means that the H matroid is this poset of the H matroid has a unique maximal element, and we can also characterize this unique maximal matroid. But the last, as I said, when H is equal to C5, there are more than one maximal C5 matroids. So this means that the value function is for C5 is not sum modular. So in general, this function is not sum modular. But still, we conjecture that the sum modularity of this value function characterizes a unique maximality. So that's our ambitious conjecture, sum modularity conjecture. So this says that the poset of all H matroids has a unique maximal element if and only if the value function is sum modular. And why this is important? So because it might give a combinatorial characterization for various class of the matroids related to the rigidity. So here are some key examples. So this is already explained. So D minus 1 cofactor matroid is KD plus 2 matroid. And if you look at the D-dimensional rigidity matroid, then Volkan's laws prove that any complete bipartite graph, KD plus 2D plus 2 is a circuit. So this means that D-dimensional rigidity matroid is KD plus 2, KD plus 2, D plus 2 matroid. And as an interesting example is D hyperconnectivity matroid by Karai, which is a KD plus 2, KD plus 1, D plus 1 matroid. this matroid also appeared in the context of the matrix completion problem by Bernstein. And here, so far, I defined H matroid on the complete graph, but there is no reason to restrict the underlying ground set to the complete graph. We can look at the different graphs. For example, if we look at the complete bipartite graphs, then the KDD matroid appears in the context of the matrix completion due to Singer and Clinch, and by rigidity matroid by Karai, Nebo, and Novik. And another ambitious conjecture is the following Graber type conjecture. So we may say, so we can pose the following conjecture. So each of the above examples in the unique maximal matroid each of the above example is a unique maximal element in its respective poset of H matroids. Okay, so if this and this are correct, then we have that this value function is gives a combinatorial characterization of those matroids. Yes, I know that this is very ambitious, but just it's nice to formulate. And currently, I have no comment about this second conjecture, but I have several comments, small observation for this first conjecture. So let me explain this. So, so we could prove this conjecture for some special case of H. So if H is a graph in this list, so we can show that the poset of all H matroid has a unique maximum element, and its rank function is equal to the value function. So here is PK denotes path of length k minus 1. And this means disjoint union of K2, C4, K3, K4, K5, K4 minus 1H, K5 minus 1H, K6 minus 1H, K1, 3. We have also an example for the combination of two graphs. And we can also prove that if H is equal to K23, or like a CK, then there are more than one maximal H matroids. And interesting case is when H is a combination of K4 and K23. Even in this case, it turns out that the poset has more than one maximum element. Okay. So this is a current result we can show. And so this general conjecture might be difficult, but probably much easier question is whether we can prove that this conjecture in the case when H is a tree. Even for this case, I do not have a complete answer. And in the proof, we use an interesting connection to the weak saturation numbers from extremal graph theory. But I will not go into the detail of this point. So if you are interested in this, then please have a look at our preprint. And before closing my talk, so let me give one particular important special case, which is a d-hyperconnectivity matroid due to Kanai. So here, in this matroid, so this matroid again is defined by using the matrix, which is very similar to the rigidity matrix. And essentially, the combinatorial structure of the matrix is the same as the rigidity matrix. But instead of Pi and Pj, we have Pj here and we have minus Pi. So Mira has a question. I think you mean that. Maybe yes, yeah. Mira asked, the question is whether the case when script H minimum circuit graphs in script H have size 5. I have not checked, but probably I agree that the when minimum circuit graph in script H have size 4, then yeah, probably we can solve the conjecture. Okay. Yeah. So let me come back to this hyperconnected matroid. Okay. And so this hyperconnectivity matroid is a raw matroid of this matrix. And this hyperconnectivity matroid also appeared recently in the context of a matrix composition problem due to Bernstein. And it is known that this matroid is KD plus 2, KD plus 1, D plus 1 matroid. So any KD plus 2 is a circuit, and any KD plus 1, D plus 1 is a circuit. And we can ask again the combinatorial characterization problem for this matroid. And when D is equal to 1, this matroid is just a cycle matroid, graphic matroid. So it's not a very interesting object. But it turns out that the combinatorial characterization problem is very difficult, even in the case when D is equal to 2. And this is still open. So recently, there is a very interesting result by Bernstein about NP type combinatorial characterization. So this gives like a tree decomposition type characterization in the context of the rigidity. But a counterpart of the Raman theorem is still open, even in the case when D is equal to 2. So the case when D is equal to 2 is a somehow interesting smallest case. In that case, we have K combination of K4 and K33. And for this case, we don't have a combinatorial characterization, but still we can solve the conjecture, submodularity conjecture. So we could prove that the following are equivalent. The poset of all K4, K33 matroids has a unique maximum element, and value function for this combination is a submodular. So those two items are equivalent. So this theorem means that if the two hyperconnective matroid is a unique maximal matroid in the poset of the K combination of K4 and K33 matroids, then this value function gives a combinatorial characterization. This also further implies that value function for the K3 with respect to the complete bipartite graph gives a combinatorial characterization of the rank function of the 2 by rigidity matroid by Karai, Nebo, and Novik, which is also equal to the matrix completion matroid of rank 2 by the Singer and Cook-Link. So that's so maybe one of the most important special case. So that's the end of my talk. So I have a lot of questions. For example, so lots of difficult questions, but I have also a much easier question. Like so, this is the one I explained already. So can we prove the Maximality conjecture in the case when H is a 3 or the minimum degree of H is at most 2? It's a slightly more difficult version. And another question is it true that every maximal KD2 matroid is an abstract D-rigidity matroid? This looks true, but I don't know the answer. I can't prove. Important open problem is how can we compute the value of the value function? Yes. So I hope there is some progress during this semantic program about those conjectures. So that's the end of my talk. Thank you very much.
Thank you, Shin-ichi. Are there any questions?
Can I ask a question, Tony?
Yeah.
Just on your second last question there, Shin-ichi, you said, is it true that every maximal K plus D2 matroid is an abstract D-rigidity matroid? So what do you have to prove there? Do you have to prove the rank?
Yes.
So you have to prove that the rank, just the bound on the rank, is it?
Rank is equal to Dn minus D plus 1 choose 2. So you can easily show that if for any KD plus 2 matroid, its rank is at most Dn minus D plus 1 choose 2. But I can't prove the equality. So this is equivalent to asking whether the matroid has a zero extension property.
But does that not follow from the fact that KD plus 2 is a circuit?
No. So there are a bunch of equivalent formulations of abstract rigidity matroids in the book of Graber, Servatis, and Servatis. And yeah. Thank you. So it looks very, it's an easy question, but looks an easy question, but I don't have a proof.
So I think we have quite a bit about abstract rigidity matroids in general, and the combinatorial rigidity book that we wrote, 93 with Graver. And there are also various characterizations of this, of abstract rigidity. In particular, what I think is important here is the characterization of the co-circuits, because how do you get a hold of the vertices? And that's sort of the opposite from the cycles. So instead of saying that all K2, D plus 2s are cycles, one could say that there are these vertex co-cycles. So the star of a vertex minus D elements is a co-circuit, and those co-circuits form the basis of the co-cycle space. So that's an equivalent characterization to Viet Hung's characterization that you mentioned here.
Yeah.
All of this, so it's quite involved. And I think that your second to last question is actually sort of buried already in what we know about the abstract rigidity matroids.
I'm not sure. So the difficulty is how to relate this equivalent formulation with the maximality in the poset. Yeah. Okay.
Yeah, I see.
Yeah.
But so what I don't quite understand is your definition of H matroid. So not every collection of graphs gives you a matroid. You cannot just freely prescribe cycles, because there's a problem here that sometimes you are forced to the minimality of cycles, that no cycle contain another, is actually not easy to see. So you cannot say any family of graphs.
We can define at least, but I'm not saying the existence of such a matter.
But some families of graphs will not give you matroids.
Yeah,
right? So any member of H need not be a minimal dependent set. If they're all dependent, the minimality is not a given. So this is just a definition, so we can define. Right, but that's what I'm saying, that if you say that definition is that every edge set of a copy of any member of H is a circuit, that I don't believe gives you a matroid, because sometimes you are forced to say that no contains another. I'm not saying that there is such a matroid. I'm just saying the definition of a matroid. So if H is very bad, then we don't have such a H matroid. Then okay, then you have. All right. Just yeah. So probably this question also contains as a special case whether the H matroids exist. Okay. So that's true. That's an interesting question. Much easier, interesting question. Can we characterize when the H matroid exists or not? Yeah, that's a good point. So it's interesting that KNs have the nice property that if you intersect KNs, there is they cannot agree in almost all the edges, right? So that is a nice thing that actually leads you to the one extension property eventually, right? And that's what you need to get your rank. Yeah. So that's why I believe for the K5, you can actually handle your question. Just show that one extension works, and then you have an abstract rigidity matroid.
So I have a question about the K3, 3, K4 matroids and like what exactly is known right now. So
what is known is
like so you know that there exists a unique there exists a unique maximal element, but you don't know that this is like the hyperconnectivity matroid.
No, even it's no. Sorry. So the current situation is even worse. So I can just prove the equivalence of those two items, but I don't know whether the poset has a unique maximal element.
Oh, okay, I see.
So what I'm saying is that if there is a unique maximal element, then its rank function is characterized by this value function.
I see. And so where did you run into difficulty with this? I'm curious.
Well, simply, I don't have any tool to prove the unique maximality.
Okay.
Yeah. The difficulty is actually that we don't have a constructive procedure for this matroids. In case of the K5 matroids, we had a nice constructive characterization for the base in the K5 matroid, cofactor matroids. And we use this for showing that the two cofactor matroid is a unique maximal K5 matroid. We don't have such a nice constructive characterization for this case.
I see. Cool, thanks.
Okay, so I had a question about, first of all, Shin-ichi, this is a very nice paper, nice talk. It gives, illuminates when unique maximal matroids might exist and when not. I was curious about this weakly saturated sequence. It seems like, tell me if I'm wrong. It seems like when you're showing, I mean, of course, you're showing in many cases that things are not unique, and that's not what my question is about. It's when you show that a maximal matroid is unique, it seems like there are some results that you have, I just looked at your archive, by the way, that rely on this weakly saturated sequence and do not require a representation. But there are other results like the cofactor one and all the bipartite ones that actually require a representation to prove the uniqueness. Can you tell us when you need the representation and when the simple result using this weakly saturated sequence, which does not seem to need a representation, what sort of separates the two, when you can use one and when you can't?
I don't have an answer, but currently, so what I can say is that the results from the weakly saturated sequence can be only used when we know only when our target matroid is a very simple structure. And for example,
by which you mean, what is the target matroid? You mean the final unique maximal matroid?
Yeah,
that's what you mean?
So
yeah.
Usually we guess the final unique maximal matroid first. And we try to show that for this matroid, we have the rank function is equal to this value function. And for showing this, we can use the results from the weakly saturated sequence. But this is only possible when the flat of the target matroid has a very simple structure. It's because the result on the weakly saturated sequence are also very limited. So probably we can still we may have even more like results. Just we recently learned this connection, so maybe we'll have more.
This connection with the flats, you mean?
This connection of our value function to the weakly saturated sequence.
I see.
From the extremal graph theory.